Beneath the quiet, fog-covered cliffs of Northern California's Lost Coast, in one of the most seismically restless patches of ground in the entire country, scientists have just found something that was never supposed to be there. It isn't a new fault. It isn't a crack opening in the earth. It's an entire slab of ancient ocean floor, a leftover fragment from a tectonic plate that mostly vanished from the surface of this planet tens of millions of years ago, quietly stuck to the underside of North America and sliding sideways beneath it like nothing else geologists have documented in this region before. Researchers have named it the Pioneer Fragment, and the reason it matters isn't just that it's old or strange or hidden. It's that this exact piece of buried crust appears to explain one of the most puzzling earthquakes California has ever produced, and it means the hazard map for one of the most dangerous stretches of coastline in America has to be redrawn. Stick with me, because what's actually moving down there, how scientists found it, and what it means for the millions of people living above it is a genuinely fascinating piece of detective work, not just another scary headline. If earthquakes, hidden faults, or strange geology like this genuinely interest you, drop a comment and let me know, because it shapes what gets covered here next, and I rate every single one. And if you want the next deep dive the moment it's ready, go ahead and subscribe now, because this particular story is still actively unfolding, with new details expected over the coming months as researchers dig deeper into exactly what this fragment is doing down there. Now, let's get into it. To understand why this discovery is such a big deal, you first need to understand the specific patch of ground it was found beneath, because this is not an ordinary stretch of coastline. Just offshore from Cape Mendocino, in the far northwestern corner of California, three of Earth's major tectonic plates collide in a single chaotic meeting point known as the Mendocino Triple Junction. It is one of the most seismically active locations in the entire United States, a place where the rules that usually keep tectonic plates moving in predictable, well-understood directions simply don't apply cleanly. The Pacific Plate is sliding sideways past the North American Plate here, which is exactly the motion that produces the San Andreas Fault, California's most famous fault line, running south from this junction for hundreds of miles. At the same time, a much smaller plate called the Gorda Plate is diving underneath the North American Plate immediately to the north. And that collision is the southern tip of the Cascadia Subduction Zone, the same fault system responsible for the catastrophic magnitude 9 earthquakes that periodically devastate the entire Pacific Northwest. So right at this one triple junction, you have strike-slip motion, subduction, and continental collision all happening within a few dozen miles of each other. Geologists have studied this junction for decades, and until now, they believed they had a reasonably solid grasp on how these three plates interact. That confidence just took a serious hit. The story really starts back in 1992 with an earthquake that never fully made sense. On April 25th of that year, a magnitude 7.2 earthquake struck the Cape Mendocino region, tearing through buildings, triggering landslides, generating a small tsunami, and causing tens of millions of dollars in damage across the surrounding communities. Large earthquakes happen in this region often enough that, on its own, this wouldn't necessarily have stood out as a mystery. What stood out was the depth. When seismologists located the epicenter, they found it sitting at only about 10 kilometers below the surface, roughly 6 miles down. That's remarkably shallow for an earthquake of that size in this particular setting, because the subducting Gorda Plate, the slab everyone assumed was responsible for earthquakes in that exact spot, was known to be sitting at least twice that deep at that location. In other words, the earthquake happened in a place where, according to the existing models, there wasn't supposed to be a fault capable of producing something that large. For over 3 decades, that mismatch sat there as an open question in seismology, an anomaly nobody could fully explain. Some researchers propose the existence of what's called a slab gap, a shallow pocket formed by friction as one plate drags against another, theoretically allowing hot mantle material to well up into that gap and generate earthquakes on its own. It was a reasonable hypothesis, but it was never confirmed, and it never quite closed the case. The other possibility, the one that has now been confirmed, was that there was something else entirely sitting down there. Not a gap, not magma welling upward, an actual physical fragment of tectonic plate stuck in a place nobody expected to find one. Here is where the actual discovery gets interesting, because finding a hidden slab of crust 10 kilometers underground isn't something you can just go dig for. You can't see it. You can't drill down and confirm it directly, not at this scale, not with any reasonable amount of resources. Instead, a team of researchers from the United States Geological Survey, the University of California, Davis, and the University of Colorado Boulder, led by USGS geophysicist David Shelley, had to listen for it. Their method involved something called low-frequency earthquakes, a category of seismic event so weak that no human being could ever feel one, thousands of times fainter than anything that registers on your senses standing on the ground above. These tiny tremors happen constantly in places where underground rock surfaces are grinding slowly against each other, releasing small amounts of stress in a nearly continuous trickle rather than one dramatic rupture. Individually, each one of these events tells you almost nothing. But by using a dense network of seismometers spread across the region and recording an enormous volume of these faint signals over time, then digitally stacking thousands of them on top of each other, researchers can start to build something close to an X-ray image of what's actually moving underground, tracing the precise depth, shape, and motion of structures that are otherwise completely invisible from the surface. When Shelley's team pointed this technique at the region just south of where the Gorda Plate dives underneath North America, they found a swarm of these low-frequency tremors clustered at a depth of roughly 10 kilometers, generated by something moving sideways rather than diving downward. That sideways motion was the key detail. A subducting slab moves down and under. What the team was detecting was a separate body of crust, shallower than the main subducting plate, sliding horizontally along its own distinct boundary. They named this newly identified body the Pioneer Fragment, and the story of how it got there connects all the way back to a tectonic plate that mostly disappeared from the Earth's surface millions of years ago. The Gorda Plate, the piece currently subducting beneath the southern end of Cascadia, is itself one of the last surviving remnants of a much larger plate called the Farallon Plate, which once ran along nearly the entire length of California's coastline. Over tens of millions of years, the vast majority of the Farallon Plate was consumed, pulled down into the mantle as the Pacific Plate and the North American Plate rearranged themselves around it. But not every piece of a subducting plate goes down cleanly. Sometimes, as one slab grinds past or beneath another, a smaller chunk can get sheared off, trapped, and effectively pasted onto the underside of the plate riding above it, rather than continuing its journey down into the mantle. That appears to be exactly what happened here. A fragment of the old Farallon Plate got stuck to the base of the North American Plate as the region's tectonics reorganized around it, and instead of sinking, it has been quietly dragged along sideways ever since, essentially hitching a ride, like a piece of gum stuck to the underside of a shoe that keeps scraping along the pavement no matter which direction the shoe walks. That description actually comes directly from the researchers themselves. And it's a genuinely useful way to picture what's happening. This isn't a plate behaving the way plates are supposed to behave in a textbook diagram. It's a leftover piece, riding along for tens of millions of years, generating its own distinct earthquake activity along the boundary where it grinds against the rock above it. And that boundary is the real headline here. By identifying the Pioneer Fragment, the research team has also identified something arguably more important, a previously unknown, nearly horizontal fault running along the contact between this fragment and the North American Plate above it. That fault line sits at a shallow enough depth to explain exactly the kind of earthquake that struck Cape Mendocino in 1992, and it had never appeared on any hazard map before, for the simple reason that nobody knew it was there. As one of the researchers, geophysicist Catherine Materna, put it plainly, it had always been assumed that faults in this region follow the leading edge of the subducting slab, but this example breaks that assumption entirely. The plate boundary, in her words, simply isn't where scientists thought it was. If that discovery stood alone, it would already be significant. But the team found something else while mapping this region, and it complicates the picture even further. What had long been described as a triple junction, a meeting point of three tectonic plates, now effectively behaves more like a five-way intersection, once you account for hidden pieces like the Pioneer Fragment. Beneath the southern end of the Cascadia Subduction Zone, the researchers identified yet another buried fragment, this one a broken-off sliver of the North American Plate itself, currently being dragged downward into the mantle alongside the sinking Gorda Plate. So, in this one relatively compact stretch of coastline, geologists now have to account for at least 5 distinct pieces of crust interacting with each other simultaneously, rather than the 3 clean plates the textbook version of this junction has described for decades. Each of those additional pieces represents its own potential source of earthquakes, behaving according to its own physical properties, at its own depth, along its own newly discovered boundary. It's worth taking a moment to actually walk through what happened on the ground back in 1992, because it helps explain why solving this 30-year-old mystery carries real weight, rather than being purely academic. The earthquake struck on the morning of April 25th, centered just offshore from the small town of Petrolia, and it was powerful enough to be felt across a huge swath of Northern California. Buildings in the town of Ferndale, one of the closest population centers, suffered serious structural damage, with facades collapsing onto parked cars and streets. The shaking triggered landslides across the steep, unstable terrain that defines much of this coastline, and it generated a small tsunami that added yet another layer of danger for coastal residents already dealing with collapsing structures and damaged roads. Total damage estimates ran as high as $75 million, a substantial figure for a rural, sparsely populated stretch of coast. and the event was followed by 2 more major aftershocks within the following days, each large enough to cause additional damage on their own. For 3 decades, seismologists studying this event kept running into the same wall. The numbers didn't add up cleanly against the models they had. Now they finally do. To really appreciate how the detection method itself works, it helps to understand what makes low-frequency earthquakes so different from the kind of earthquake most people picture when they hear the word. A typical earthquake happens when stress along a fault builds up until it exceeds the strength of the rock holding it in place and then releases suddenly, all at once, in a matter of seconds. Low-frequency earthquakes are almost the opposite. They occur when 2 rock surfaces are sliding past each other slowly and somewhat continuously, releasing small pulses of energy over and over rather than one dramatic snap. Individually, each pulse is almost meaningless, far too weak to register as anything more than background noise on a single instrument, and far too weak for a human being standing directly above one to ever notice. But because these events repeat so often, sometimes generating thousands of tiny pulses over the course of a study period, researchers can use statistical techniques to combine or stack huge numbers of these faint signals recorded across a dense network of seismometers. Stacking essentially averages out the random noise while reinforcing the signal that's consistently present across many instruments, gradually sharpening a blurry picture into something with real usable precision. It's a bit like taking thousands of slightly shaky, low-light photographs of the same object and combining them digitally until a clear image emerges from what would have been unusable noise in any single frame. That is, in simplified terms, how a team of scientists were able to trace the exact depth and motion of a fragment of tectonic plate that no one could ever physically see or drill down to directly. It's worth pausing here to actually explain why any of this matters beyond pure scientific curiosity, because the practical stakes are significant. Seismic hazard maps, the tools that inform building codes, insurance rates, infrastructure planning, and emergency response strategy across an entire region are built on models of where faults exist, how deep they sit, and how they're expected to behave during a rupture. Every one of those models for this stretch of California was built without any knowledge that the Pioneer Fragment existed. That means the shallow horizontal fault running along its boundary with the North American plate was, until this study, functionally invisible to the planning process. Matthew Herman, a geophysicist at California State University, Bakersfield, who wasn't involved in the study, described the broader lesson clearly. Scientists have tended to treat triple junction regions as a relatively simple intersection of 3 straightforward plate boundary styles. And this research is part of a growing body of work showing that this simplified picture doesn't hold up. You cannot fully understand the hazard in this region without understanding exactly how the Cascadia Subduction System interacts with the San Andreas Fault system at a level of detail nobody had access to before. And critically, Herman pointed out that the Pioneer Fragment may pose a genuinely different type of earthquake hazard than scientists have historically expected in this area, precisely because it doesn't behave like the subducting slab everyone has spent decades studying and modeling. Now, it's important to be precise about what this discovery does and does not mean, because it would be easy to walk away from this thinking a brand new fault just appeared out of nowhere, ready to unleash some unprecedented disaster. That's not what happened. This fragment has been sitting exactly where it is, moving exactly the way it moves, for a very long time, likely tens of millions of years. Nothing about the Earth changed recently. What changed is that scientists finally developed the tools sensitive enough to detect it. The 1992 Cape Mendocino earthquake wasn't a warning sign of something new stirring beneath California. It was, in hindsight, the fragment doing what it's apparently been doing all along, generating shallow earthquakes along a boundary nobody could previously see. The genuine significance of this discovery isn't that the danger just increased overnight. It's that the danger was already there, hidden, unaccounted for. And now, for the first time, it's visible enough to actually be studied, modeled, and planned around properly. That distinction matters enormously because it's the same pattern that keeps showing up across earthquake science more broadly, and it's worth taking a moment to place this discovery in that wider context. Because the Pioneer Fragment isn't the only thing researchers have recently found lurking beneath California that older models missed entirely. Just a few months after this study, in the summer of 2026, a separate team led by researchers at the University of Bern published findings showing that stress levels along the San Andreas and San Jacinto fault systems in Southern California have reached their highest point in roughly 1,000 years, based on a physics-based model built from radiocarbon dating, tree ring records, and historical observations stretching back centuries. That same research identified something the team is calling an earthquake gate, a junction near Cajon Pass, northeast of Los Angeles, where the San Andreas and San Jacinto faults meet in a way that could allow a rupture, starting on one fault to jump onto the other, turning what might have been a single contained earthquake into a much larger multi-fault event capable of threatening the Los Angeles Basin, San Bernardino, Riverside County, and the Coachella Valley simultaneously. And, separately from both of those findings, researchers at Oregon State University spent years analyzing deep sea sediment cores near this same Mendocino region, and found evidence that a major Cascadia Subduction Zone earthquake and a major northern San Andreas earthquake have ruptured together within minutes to hours of each other, at least 10 times over the past 3,100 years. Individually, each of these findings is a meaningful piece of new science. Together, they paint a consistent picture. The fault systems running through California and the Pacific Northwest are more interconnected, more complex, and less fully understood than the models built even just a decade ago assumed. And 2026 has turned into a genuine turning point year for recognizing exactly how much was hiding beneath the surface, sometimes literally. It's worth spending a little more time on that Cage Unpassed finding specifically, because the underlying concept, an earthquake gate, is one of the more genuinely unsettling ideas to come out of California seismology in recent years, and it pairs naturally with the kind of hidden structure discovery the Pioneer Fragment represents. Most people who think about the San Andreas Fault picture it as a single continuous crack running the length of the state. But in reality, it behaves as a series of distinct segments, and earthquakes usually stay contained within one segment rather than tearing through the entire fault at once. What researchers found near Cajon Pass, where the San Andreas meets the smaller San Jacinto Fault roughly 50 miles northeast of downtown Los Angeles, is that under the right stress conditions, a rupture beginning on one of these faults could potentially jump across the junction and continue rupturing along the other, effectively merging two separate smaller earthquakes into a single, far larger one. Geologist Kate Scherer, a co-author on that study, explained that because such a long time has passed since either fault system has produced a major earthquake, the accumulated stress sitting along both of them right now is substantial, and the research team's modeling suggests the conditions needed to unlock that gate are currently in place. Whether that gate stays shut for another few decades or opens at some point is not something any current model can specify with precision, and that uncertainty is exactly the point. It's another example of a hazard that existed in the underlying rock all along, only recently mapped clearly enough to actually understand. There's also a slower, quieter discovery worth mentioning here, because it adds another layer to the picture of California's shifting underground geology, even though it operates on an entirely different timescale and through an entirely different mechanism. A few years ago, seismologists at the Cooperative Institute for Research in Environmental Sciences and the Scripps Institution of Oceanography, while studying decades of earthquake records across California, noticed something unusual happening beneath the Sierra Nevada mountain range. Earthquakes were occurring at depths roughly twice what's typical for that part of the crust, in a zone where the rock should ordinarily be too hot and under too much pressure to fracture and produce seismic activity at all. After digging into the pattern, researchers concluded they were witnessing rare, direct evidence of a process called lithospheric dripping, essentially dense portions of the Earth's outermost rocky layer slowly peeling away and sinking down into the mantle beneath the mountains, a fundamental continent-shaping process that geologists had modeled theoretically for years, but had almost never caught happening in real time with this kind of clarity. It's a completely different mechanism from the Pioneer Fragment, operating on a much slower timescale and not directly tied to the same earthquake hazard, but it reinforces the same broader theme running through basically every major geological discovery to come out of California in the last couple of years. The ground beneath this state is nowhere near as fully mapped or as fully understood as most people, including most scientists working in adjacent fields, previously assumed. So what does all of this actually mean for the people living above these fault systems right now? It does not mean an earthquake is coming tomorrow, or that the discovery of the Pioneer Fragment has somehow raised the immediate day-to-day risk of something happening this week. Nothing about the underlying physics changed the moment this paper was published. What changed is the accuracy of the map. And an accurate map is not a reason for panic. It's the foundation every meaningful safety improvement in earthquake-prone regions has ever been built on. This is worth saying clearly because it's the same lesson that keeps showing up again and again throughout the history of seismology. The 1989 Loma Prieta earthquake, the 1994 Northridge earthquake, and plenty of other major California quakes each exposed gaps in the hazard models that existed at the time. And each time, the response wasn't to throw up hands in despair. It was to update the building codes, refine the emergency planning, and improve the monitoring networks based on exactly what the new evidence showed. That is precisely the cycle this discovery feeds into. Researchers studying the Pioneer Fragment are now working to determine exactly how far it extends, how much strain is currently accumulated along its newly identified boundary with the North American Plate, and what magnitude of earthquake it might realistically be capable of producing on its own, separate from the subduction zone earthquakes everyone has already been planning for. That work will take time, but the fact that it's now possible at all, that scientists can even ask these specific questions with any confidence, is a direct result of the low-frequency earthquake detection techniques that made this discovery possible in the first place. Techniques that are still improving year over year as seismometer networks across the region get denser and computing power available for stacking and analyzing. Tremor data keeps increasing. It's genuinely remarkable, if you step back and think about it, that researchers can locate a slab of ocean floor from a tectonic plate that mostly vanished tens of millions of years ago, sitting 10 kilometers underground, invisible to the naked eye, and undetectable by any direct physical inspection, purely by listening to earthquakes thousands of times too faint for a human being to ever feel. That is the kind of scientific capability that simply did not exist a generation ago, and it's continuing to reshape how seismologists think about seemingly well-studied regions all over the world, not just this one stretch of Northern California coastline. If you find that as fascinating as I do, that's exactly the kind of story worth sharing with someone who'd appreciate the actual science behind a headline like this instead of just the scary version of it, so feel free to pass this along. And if you want to stay updated as researchers refine exactly how large and how active this fragment actually is, subscribing means you won't miss it when the next round of findings comes out. It's also worth addressing directly why a discovery like this doesn't automatically translate into a bigger earthquake or a higher magnitude ceiling for the region, because that's a natural assumption and it isn't quite right. Finding a previously unknown fault boundary changes where scientists expect certain earthquakes to originate and how shallow they might be, which affects how strongly the shaking is felt at the surface directly above it, but it does not, on its own, change the fundamental amount of tectonic energy being generated in the region as a whole. The Pacific, Gorda, and North American plates are still moving relative to each other at the same rates they always have. What's different is that some of the strain being released along the way has now been correctly attributed to a specific, shallow, previously invisible structure, rather than being lumped in with the deeper subducting slab or dismissed as an unexplained anomaly. That's a subtle but important distinction, because it means this discovery is fundamentally a story about improved precision in understanding an existing hazard, not evidence of some new source of energy or danger that wasn't there before. The 1992 earthquake already happened. The Pioneer Fragment didn't get more active because scientists found it. Scientists simply finally figured out what had been generating quakes like that one all along. For people living in or around Northern California, and really across any earthquake-prone region on the West Coast, the practical takeaway from a discovery like this isn't a new item to panic about. It's a reminder that the baseline level of preparedness that already made sense before this study is still the right level of preparedness now. Knowing your home's evacuation routes, securing heavy furniture and water heaters to prevent injury from falling objects, which remains one of the leading causes of harm during earthquakes, keeping several days of emergency water, food, and basic supplies on hand, and having a family communication plan that doesn't depend entirely on cell networks are all steps that matter, regardless of which specific fault ends up rupturing first. What discoveries like the Pioneer Fragment actually change is not what individuals need to do differently tomorrow. It's what emergency planners, structural engineers, and hazard modelers need to account for as they continue updating the frameworks the rest of us rely on without ever thinking about them day to day. There's also a broader scientific story unfolding here that goes beyond just California, because the method used to find the Pioneer Fragment, tracking swarms of low-frequency, imperceptible earthquakes to reconstruct hidden subsurface structures, is now being applied to other complex tectonic junctions around the world where similar mysteries have lingered for decades. Triple junctions, the meeting points of 3 or more tectonic plates, exist in a number of seismically significant regions globally, and many of them share the same historical problem this study just solved: earthquakes that don't quite match the expected depth or location predicted by simplified plate models. As this low-frequency tremor mapping technique gets refined and applied more widely, it's entirely plausible that other hidden fragments, other invisible fault boundaries, are waiting to be found in other parts of the world using the exact same approach. In that sense, what happened beneath Cape Mendocino isn't just a regional story about one stretch of California coastline. It's a demonstration of a genuinely new way of seeing into the Earth's crust, one that's likely to keep producing discoveries like this one for years to come as the technique gets pointed at other long-standing geological puzzles. Stepping back to look at the full picture, what researchers have actually found beneath Northern California is a fragment of ancient ocean crust, a remnant of a tectonic plate that largely disappeared from the surface of this planet millions of years before modern humans existed, still quietly grinding along beneath one of the most densely populated and economically important coastlines in the country. It has likely been there, moving in roughly the same way, for an extraordinarily long time, generating earthquakes that seismologists have been recording and puzzling over for more than 3 decades without fully understanding their source. What changed in January of 2026 wasn't the geology itself. It was our ability to finally see it clearly, using a method sensitive enough to detect motion happening 10 kilometers underground, through nothing more than the faint, imperceptible tremors it leaves behind. That is not a story about a hidden threat suddenly appearing out of nowhere. It's a story about scientific tools finally catching up to a reality that has existed all along, and about how much of the ground beneath even the most heavily studied regions on Earth remains genuinely unmapped, waiting for the right technique and the right team to finally bring it into focus. It's a genuinely strange feeling to sit with, honestly. The idea that a region seismologists have poked and prodded and instrumented more thoroughly than almost anywhere else on the planet could still be hiding something this fundamental. Northern California isn't some remote, under-monitored corner of the world. It sits within reach of some of the best-funded, most advanced earthquake research institutions anywhere, and the San Andreas Fault has arguably been studied more intensively than any other fault line in human history. And yet a slab of ancient seafloor was sitting there, moving, generating real earthquakes that damaged real buildings for who knows how many decades, without anyone being able to say for certain it existed. That's not a failure of the scientists who came before. It's simply a reflection of how difficult it genuinely is to see clearly into solid rock, and how much progress in this field depends on patiently waiting for new tools, new sensor networks, and new computational methods to catch up with questions that have been sitting unanswered for a very long time. So here's a question worth sitting with, and I'd genuinely like to hear your take on it in the comments. If a fragment of tectonic plate that's been moving beneath one of the most studied earthquake zones in the world could stay completely hidden until a new detection method finally revealed it, decades after the earthquake it likely caused, what else is still sitting undiscovered beneath the ground you're standing on right now? That's not a rhetorical scare tactic. It's a genuinely open question in earth science, and it's part of why stories like this one are worth paying attention to. If this helped you understand the actual mechanics behind a headline that's easy to skim past without grasping what it really means, share it with someone who'd find the detective work behind it as interesting as you did. And subscribe, so you catch the next update, the moment researchers report back on exactly how large the Pioneer Fragment turns out to be, and exactly what kind of earthquake it's capable of producing on its own. We'll be tracking it closely as the data comes in.